let's start. So up to this point, we considered always the case where we have few parameters to learn and many data. And we have seen that in that case, things work well. We can have good estimates of the parameters. And we can estimate how many data we need to have good estimates of the parameters. So now what I would like to do today and tomorrow is to discuss what happens when you have many parameters and many data. So can you still learn your parameters or not? And how many data you need to be able to learn your parameters. And to discuss this, we will consider the simplest case, which is Gaussian variables and essentially principal component analysis. So I will do this today, and then I would like to discuss what happens if you try to make it sparse, so if you try to reduce the number of parameters. And as usual, I will show you an application to some biological data. And then next week, I would like to move to the problem of inferring more precisely interactions between variables. So, okay, this will be next week. So when you have many parameters and many data, many parameters, I mean parameters that scale with the number of data somehow. So you don't fix the number of parameters and increase the number of data, but you increase both at the same time. We are in the regime of what is called high-dimensional inference, okay? High-dimensional inference. And so the simplest case is the case of Gaussian variables. So let's consider data, y. So y is, as usual, a vector with L dimensions. L is the length of our data. And we can assume that these data are generated by a Gaussian distribution. So the probability of y given a matrix T, so T is a L by L matrix. The probability is a Gaussian, so a multivariate Gaussian, which is defined as the square root of the determinant of T divided by 2 pi to the power L over 2 times the exponential of -1/2 y transpose times T times y, okay? Where this means sum over ij of yi tij yj, okay? And the matrix T is an L by L matrix that is symmetric. It must be symmetric because, I mean, if it is not symmetric, it will be symmetrized by this sum, so the anti-symmetric part will disappear. And also, for this, for the normalization of this quantity to be well-defined, so for this to be well-defined, it has to be also positive definite. Otherwise, if you have negative eigenvalues of T, of course, you have directions where the exponential will diverge and you cannot normalize your distribution. Okay, so we assume that our data are generated by this multivariate Gaussian, and our goal is to learn the matrix T. So now we have many parameters, we have L squared over 2 parameters essentially. If you have Gaussian variables, you can, okay, and I assume here that the mean of the variables is 0 for simplicity. If it is non-zero, you can always subtract the mean and go back to this. So let's make it simple. Now, if you have, so the mean is 0, what you can compute is the correlation of the variables. So let's call this C hat. hat means this is the true one, right? T hat is the true T, the one that is used to generate the data, and C hat is the true correlation of the data. So this is equal to the integral over y of P of y given T times yi yj. And now it's a Gaussian integral. You can do it. I will not do the calculation, but what you get is that the matrix of correlations is the inverse of the matrix T. So, okay, the data are correlated according to T, to the inverse of T. So now, if you diagonalize T, so if you move to the basis where T is diagonal, then you will have eigenvalues and eigenvectors of T. So let's call them lambda k hat and ek hat. So these are the eigenvalues and these are the eigenvectors. So it is a symmetric and positive definite matrix, so the eigenvalues are positive, the eigenvectors make an orthonormal basis of the space, and now this probability in the basis where T is diagonal becomes just a product of independent Gaussians, right? So you get a product over K from 1 to L of the exponential, sorry, just to keep the notation consistent with my notes, let me say that these are the eigenvalues and eigenvectors of C. So of course, if T is diagonal, C is also diagonal. And let's say that these are eigenvalues and eigenvectors of C. So then the eigenvalues of T are 1 over lambda. And our distribution becomes just the sum of yk square divided by lambda k, normalized by square root of 2 pi lambda k. Okay? So now, and the yk are the projections of y on the vectors ek, right? So if you make this change of basis and you look at the projections of your data on these eigenvectors, these are independent random variables, and the variance of yk is given by lambda k. So the bigger is lambda k, the bigger is the variance of your yk. Okay, so we would like to know if we have m samples. So now, let me see, what can I erase? Maybe let's keep this. So now if I have m samples from this distribution, can I learn T? And in particular, can I learn the eigenvalues and eigenvector of T? Because this is what I'm mostly interested in, because this is the basis where things are simple. Okay? So let's assume that, that I have, as usual, I have m data points that I collect in a matrix Y. So this is a matrix of size m times L, where each line is a vector Y. So I have m data, and each of them is of length L. I put them in a matrix. Now what I can do, of course, is I can compute the correlation C from the data, right? So my correlation Cij will be estimated as 1 over m times the sum over mu, yi mu, yj mu. And this is the empirical correlation matrix. So this is the expectation over the data of yi, yj. I can write this matrix C simply as 1 over m times y transpose y, right? Y is M times L, so Y transpose is L times M, and this is M times L, so I get an L by L matrix that gives me the correlation between two components of Y. So if I want to infer T, what can I do? I will just do Bayesian inference, and if I do Bayesian inference with a flat prior, this is basically the same as maximizing the likelihood because the prior is constant, right? And if I do Bayesian inference and I do maximum a posteriori estimate and I have a flat prior, in the end I'm doing maximum likelihood. So what is the likelihood of the data? Let's write, I will write it as L. This will be the log likelihood of the data. So it will be 1 over m times the logarithm of the probability of the data given t. Okay? So what I'm doing is I want to infer t. So t hat is the true one. T is my estimate. So what I do is, okay, I do Bayesian inference. So I know the model. I know that the y are Gaussian, but I don't know t. So I say, okay, this is my model with t instead of t hat. Now the posterior is p of y given t times p of t. I take p of t to be flat, so constant. The normalization is not important. I want to maximize the posterior, so what I have to do is to maximize this thing. And I assume that my data are IID samples from the distribution, so the probability of all the data will be the product of the probabilities. And so this is going to be 1 over m times the sum of the probability of each of the data points, right? And then I use the Gaussian. So I throw away constants because I want to maximize this, so the constants are not important. So I get 1 over m times the sum over mu. When I take the log, I have minus 1/2. Here I have sum over I of and j of yi, tij, yj. And then I have plus 1/2 times the logarithm of the determinant of t. Okay, this is when I take the log here, I have the log of the determinant to square root of it, so I have a 1/2. And when I take the log of the exponential, I get this. And sorry, here there is mu. So now I have to average this over mu. So this is constant, it doesn't depend on y, so I get 1/2 log that t. When I sum over m and divide, when I sum over mu from 1 to m and I divide by m, this is just constant, it's a constant and the sum gives 1. And then I have minus 1/2 times the sum over ij of tij. And here I have the sum over mu of yi mu, yj mu divided by m, which is c, right? So I get tij. Okay? So in the end, the likelihood is just 1/2 log that t. And this term is minus 1/2. And this is the trace of t times c, right? Minus 1/2 trace of t times c. Okay? So if I want to maximize the likelihood, what do I get? I have to do the derivative. So, okay. So if I do the derivative of L with respect of one of the matrix elements, I have to do this derivative. So, okay, the derivative of log that c is given by t minus 1 ij. You can show it. It's a simple calculation, but let's not do it. So when you take the derivative of this, you get t minus 1. And here, when you take the derivative with respect to tij, you get cij. So this is the derivative of the likelihood. It must be equal to 0 if I want to maximize. So I get my estimator for t T star, which is just the inverse of C. Okay. So let's write it here. So if I want to do Bayesian inference under the assumptions I enumerated before, what I get is that my maximum likelihood estimator is just the inverse of the empirical correlation matrix that I extract from my data. So it's very simple. Now the question is this estimator reliable? I mean, do I get something good out of it? So now what we want to understand is how many data I need for this estimator to be a good estimate of the true T, right? Okay. Yes?
Sorry. How did you write the derivative of L with respect to Tij?
Yeah. Yes, sorry, I skipped a step. So this is L. The derivative, so this is the derivative with respect to a matrix element of log that T is equal to the matrix element ij of the inverse of T. Actually, ji but T is symmetric. So, this you have to do the calculation, but it's a bit boring. So, if you want, I can write it down and okay. So this is a known result of a matrix, and then the derivative of this is just I do the derivative. This is sum over ij of Tij Cij. So when I take the derivative with respect to T, I just get C. Okay? Okay, so I get T minus 1 from this, I get C from this, and then I get T minus 1 is equal to C, and so T is equal to C minus 1. So, okay, so now the question is, how many data do I need for this to be a good estimate? Now, let's look at this C. So if I have an infinite number of data, this will converge to the true C. Okay, so this will be equal to the true C, the one that is the inverse of the true T. This is when M is infinite. If I have finite number of data, what do I get? I will have a correction. Now this is the average of many terms, yi, yj. Each yi, yj is a random variable that is independent and identically distributed. So from the central limit theorem, this must be equal to its statistical average, which is C, that I get in the infinite M limit, plus a correction, let's call it Z. So this will be Cij, and then I have a correction divided by square root of M, right? And this random variable that gives me the correction, according to the central limit theorem, is it's a Gaussian with zero mean and variance equal to the variance of one of the variables that I am averaging. Okay? So this will be let's say, the variance of yi, yj. Okay? So in order to know the variance of this quantity, I have to compute the variance of yi, yj. What is the variance of yi, yj? Well, this is easy. I have to compute the expectation of yi square, yj square, minus the expectation of yi, yj square, right? So the expectation of yi, yj is the true correlation of yi, yj. So this is equal to C hat ij. How do I get this? Well, now again, this is a result for Gaussian variables. When you want to compute the average of more than two Gaussian variables, you have a rule which is called the Wick rule, if you want, or if you want to do the average of yi, yj, yk, yl. What you have to do, and again, I will not prove this, but I can provide you references if you want. What you have to do is to pair the indices, okay? Make pairs. So this will be yi, yj times yk, yl, when you pair I with j and k with l, plus y with k and j with l, and so on and so forth. So in this case, if you have 4, you get another term that is y with l and j with k. Okay? So if I want to do yi square, yj square, I have 2i and 2j. So what I get here is I can pair I with I and j with j. So I get cii, cijj. Because every time I get this is cij hat, the true one. So if I pair I with I and j with j, I get this. And then I can pair I with j. And there are 2 ways of doing it. I can do I with one j or I with the other j. And in both cases, I get cij square. Then I have minus cij square. So this correlation, this is going to be cii cjj minus cij square. Okay? So this is some number. We can put it here. Okay? And so this calculation tells me that when I compute, if I have m data, m large enough, but not infinite, then the empirical correlation is going to be the true one plus a random correction of order 1 over square root of n, m, with a variance that is of order 1, right? This is a random variable of order 1 with 0 mean and finite variance, and okay. So can I erase this? Maybe we don't need this anymore. So, okay, you see, if I have enough data, the Cij that I estimate will approach the true ones. The problem is that there are many matrix elements. There are L square matrix elements. I mean, L square over 2 if the matrix is similar. L times L minus 1. L times L plus 1 over 2 because there is also the diagonal. So the problem is, can I mean, when I, for example, invert C, or when I try to compute the eigenvalues and the eigenvectors of C, do I get meaningful results? So, okay, maybe we can move this here. So Zij is a random variable with this So let's try to see what happens to the eigenvalues, for example. So the idea is that C, if I know the eigenvalues and the eigenvectors of C with good precision, I can invert the matrix. And I can get T with good precision. So let's use perturbation theory, because the idea is that C is equal to C hat plus a small correction, a correction of order of 1 over square root of m. So I can use perturbation theory. I hope you have seen perturbation theory of matrices in quantum mechanics, for example. So anyways, you apply the recipe. The recipe of perturbation theory is that if a matrix C is equal to C hat plus a perturbation, then the eigenvalues lambda of C are equal to the eigenvalues lambda hat of C hat plus a correction. So what is the correction? So here 1 over square root of m is the small parameter. So you get 1 over square root of m times the matrix element of the perturbation. So this is going to be the perturbation to the, the matrix element of the perturbation matrix on the eigenvector E associated to lambda. And then you have another term, which is the second order correction, which is 1 over m, because you get the square of the perturbation, times the sum over k different from L of the matrix element of the perturbation square, so EK Z EL square, divided by lambda k minus lambda L minus lambda k. And then you get terms of order 1 over square root of m cubed, and so on and so forth. Let's stop here. Let's look at the magnitude of these terms to understand if they are small. We would like this term to be small in such a way that the eigenvalues of C are close enough to the eigenvalues of to the true ones. Okay. So this term is small. This term is small because Z is a matrix. It's a random matrix, but with elements of order 1. So if you do a matrix element, this will be of order 1 divided by square root of m. So this one is small. Okay. But the problem is this one, the next one. So what's the magnitude of this term? This term is of order 1. Again, it's a matrix element of Z, and Z is of order 1. So this is a matrix of order 1. I take a matrix element. I get a number of order 1 square. So this is a positive number. This one is also of order 1 in most cases, because the eigenvalues of C are going to be numbers. We will see later that, okay, C has a certain spectrum. And typically, the difference between two typical eigenvalues will be of order 1. There will be some eigenvalues that are close, so the spacing can be of order 1 over L, but in most cases, it will be of order 1. The problem is that, so this term is of order 1. The problem is that there are L of them. So in the end, this term is of the order of L over M, because it's a sum of L terms that are not random. These are fixed numbers, and these are squares. So these are random, but they're all positive. So they will not cancel. And so this term will be proportional to L over M. Okay? The same happens for the eigenvectors. If I write the eigenvector EL of the matrix C, this is going to be equal to, according to perturbation theory, is going to be equal to E hat of L. Sorry, my L and my E are very similar. Plus, so the first correction is 1 over square root of M, sum over k different from L, of the, again, the matrix element, this time not square, divided by lambda L minus lambda k times EK, plus higher order terms. So how does this term behave? This is 1 over square root of m. But the problem here now is that this element is random. This is a random variable of order 1 with 0 mean. So with probability 1/2, this is going to be positive. With probability 1/2, it's going to be negative. This is again of order 1. So this term, if you sum L objects that have random signs, you get typically something of the order of square root of L. So in the end, all this thing is going to be proportional to the square root of L over M. So you see that you are in trouble in the sense that the perturbation is of the order of L over M. So if L over M is finite, then the correction is of order 1, and you make a mistake of order 1 on the eigenvalues and on the eigenvectors, which means even if your matrix C, each matrix element is close enough to the true, the eigenvalues and the eigenvector can be very different. Okay? So this tells you that if you want to have a good estimate of all the eigenvalues and all the eigenvectors, what you need is that M must be much bigger than L in such a way that these terms are small and the eigenvectors and eigenvalues are close to the true. Okay? So this is an example of what happens when you are in the high-dimensional regime. If L is large and if L is of the order of the data you have, which, as we will see, will be the case in many applications in biology, then you are in trouble. And you would like to know what happens when L over M is of order 1. Okay? Yes?
Can you please repeat y square root of L for the eigenvector of L?
Y I get square root of L. Yes, because here I have 1 over square root of M, and this term is a sum of L contributions. Sorry, I didn't write it, but K goes from 1 to L, because the matrix is L by L. So here I have L, I have to sum L numbers. The denominators are fixed. They are the eigenvalues of the matrix C. But the numerator is the matrix element of this Z. And Z is a random matrix with 0 mean and finite variance. So this matrix element can be positive or negative because the mean of Z is 0. And with probability 1/2, they will be positive, and probability 1/2, they will be negative. When I sum many of them, basically, okay, if you want to be precise, what you have to say is that this sum, when L is large, will basically become an integral over the spectrum of the matrix. And there are eigenvalues that are very similar, but the eigenvectors are different. So basically, for each choice of eigenvalues, you have many eigenvectors that will give you positive or negative sign. And so these positive and negative signs will cancel. And if you sum L things that are random in sign, you typically get something of the order of square root of L. So you get this square root of L.
So you say this by central limit theorem?
Exactly, yes.
And one other question.
Sure.
In the first place, why you could write the correlation matrix as a correction of the true matrix?
This?
Yeah.
Again, by the central limit theorem. So if you call yi, yj, let's say, okay, maybe I can erase this because we will not need it. I mean, I will come back to this point, but later. So it's again by the central limit theorem. So if you call x, so if you fix one matrix element, for example, 3, 4, so you take y3, y4, let's call it x. C hat is the statistical average of x. Right? And instead, C is the empirical average of M realizations of X. So C is 1 over M times the sum over mu of X mu, where you draw many times these random variables and you do the average. So by the central limit theorem, the empirical mean of M, so like if you throw a coin M times, the mean will be 1/2, let's say if it's 0, 1, the mean will be 1/2, which is the true one, plus a correction. And the correction is of order 1 over square root of M, and it's a Gaussian variable that has 0 mean and variance equal to the variance of X. Right? So the variance of this Zij is going to be equal to the variance of this thing. And the variance of this thing is what I computed before. Okay? You're welcome. Yes? Oh, you're right, sorry. Because it was +2 minus 1. Yes, thank you. Okay. So now the question is, okay, if M is much bigger than L, I have many data, and everything is fine. I'm back to the case of asymptotic inference where I have a lot of data and everything works well. But if I want to discuss the high-dimensional regime, this will be when L is proportional to M. So we can call R equal to L over M. And we assume that R is of order 1. So we have we assume that L is large, M is large, but R is of order 1. So we have many data, many parameters, and the ratio between the number of parameters we want to learn and the number of data we have is not that small. So now the discussion in general is a bit complicated, so we can restrict to the simplest case, which is when the matrix C hat, so the true correlation, is the identity. So now what I want to do is to give you an example of what can happen when you go to the high-dimensional inference limit when L and M are proportional and both large, and the ratio is of order 1. And to do so, I restrict to a simple case. The simple case is when the true correlation is equal to 1 plus S hat times a projector. So this E hat is a unit vector. E hat transpose is the projector on this unit vector. And S is a positive number. So basically what I'm saying is that this matrix C has all the eigenvalues equal to 1, except one eigenvalue that is equal to, that I call lambda 1. And lambda 1 is 1 plus S hat. And S hat is positive. So there are, all the eigenvalues are equal to 1, except 1, that is 1 plus S hat. And the associated eigenvector is this vector E hat. So I want to know if I can learn S hat and E hat from the data, okay? Before I was trying to learn all the eigenvalues and eigenvectors, and now I say, okay, let's say the matrix is the identity plus one special direction. Can I learn this special direction? So the matrix T that corresponds to this, I can write it as 1 minus S over 1 plus S hat times the same projector. Basically, this tells you that on all the vectors that are orthogonal to this, T hat is 1 and C hat is 1. And if I apply C hat to E hat, I get 1 plus S. And here I get 1 minus S over 1 plus S, which is 1 over 1 plus S. Okay? So the eigenvalues of T are all equal to 1, except one that is the inverse of this one, because T is the inverse. So the question is, can I infer S hat and E hat from M data? Okay, where I'm assuming that L and M are very large, going to infinity, with a finite ratio. Is it clear? Okay. So I go again to my Bayesian setting. So let's write again the likelihood of the data. Okay, let's not specify for the moment what are the arguments. Okay, no, let's specify. So what I do is I do Bayesian inference, again in the ideal setting where I know that the data have been generated in this way. So what I'm going to do is to assume that T, the matrix I want to learn, has the same form as T hat. So it will be 1 minus S over 1 plus S times E transpose, and I want to learn S and E. Okay? So my likelihood is the same as before. It's going to be, so same calculation as I did before. I have to estimate the logarithm of the probability of my data given my matrix, given my model. And this is 1/2 log that T minus 1/2 trace of T times C. This is the same as before. Now, if I make this assumption, the determinant of T is just, here I'm saying all the eigenvalues of T are 1, except 1, that is the inverse of 1 plus S. So the determinant is going to be, the determinant is the product of the eigenvalues, so it's 1 times 1 times 1 times 1 plus S. So this is the determinant. So I get minus 1/2 log of 1 plus s from here, minus 1/2. So when I put this expression here, I get two terms. If I put 1, I get the trace of c, but c is a constant. C is the correlation of the data, so I throw it away because it's a constant. I want to maximize. And then I get this term. So when I put this term here, I get minus 1/2 s over 1 plus s times the trace of E transpose C. Now the trace of E transpose C means I do EI, EJ, CJI, and I sum over I and j. So this is the same as E transpose C E, right? If you want by the cyclic property of the trace, you can bring this E on the other side. So in the end, my likelihood is equal to minus 1/2 log of 1 plus s minus 1/2 s over 1 plus s times the contraction of C with E. And what I want to estimate are E and S. So I have to maximize the likelihood with respect to E and S, which are my unknown parameters. So how do I do that? Well, if I want to, so E is a unit vector. So if I want to maximize the action of a matrix on a unit vector, what I have to take is the biggest eigenvalue, right? So then E star, the maximum likelihood value of E, is going to be E1, such that C E1 is equal to lambda 1 E1. And lambda 1 is the biggest eigenvalue of C. So then the likelihood, so this is for, I fix S and I maximize over this vector. And then if E is the biggest eigenvector of C, then this is just lambda 1. So when I maximize over S, what I get is minus, well, the 1/2 is a global factor, so let's put a 2 here. So I get minus 1 over S, and then I get plus S over 1 plus S squared minus 1 over 1 plus S times lambda 1. And this must be equal to 0. So you simplify the calculations, and what you get is that in the end, lambda 1, I mean S, the maximum likelihood value of S is such that 1 plus S star is equal to lambda 1, which is the solution of this thing once you simplify, okay? So what we get is that our best estimates for S and E, not surprisingly, are the principal component, which is the vector that is associated, the eigenvector associated to the maximum eigenvalue, and 1 plus S star is the maximum eigenvalue. The question now is whether these two objects have anything to do with the true ones. Okay, so these are my estimators. Are the estimators related to the true values?
Excuse me.
Yes?
Can you explain again when you substitute the EC just by lambda 1?
Why this is lambda 1? Yes, because if my estimator E is E1, then I put E1 here, okay? And then CE1 is lambda 1 E1. So this is going to be, so because in the likelihood I had E, C, E. When I maximize over E, when I want to maximize this over E, I this is maximized when E is the maximum eigenvalue. And you can see this because you can decompose C in the sum of, in the spectral representation. So you write C as a sum of projectors, and if you project on the maximum eigenvalue, you will maximize this, okay? So you replace E by E1, and then CE1 is equal to lambda 1 E1, so you get E1 lambda 1 E1, and E1 is a unit vector, so this is E1 transpose E1 is equal to 1.
So you first maximize the likelihood over E, and then again maximize like over S.
Exactly. For any S, I maximize over E, and it's always maximized by the...
Twice.
Yes. I want to maximize over both at the same time, but for any S, the maximum over E is given by the maximum eigenvector. So.
This is trace E transpose TE, right? Not just ACE. Yeah, so this should be the trace, or not?
But this is a vector, so this is not. This is a number. I can take the trace, but it's a trace of a 1 by 1 because this is a vector.
But the
C is a matrix, so this is like. If C is an L by L matrix, this is L by L. E1 is 1 by L. And E1 transpose is L by 1. So I sandwich the matrix, and so I get a number. OK? So my question is now, OK, if I do Bayesian inference, Bayesian inference tells me that the best choice is to do principal component analysis. So if I want to recover this thing, I have to take my data, compute the correlation matrix, take the maximum eigenvector, take the maximum eigenvalue, and these are my estimates for E and S. And the question is, are they related to the true ones? So to do that, we need to study the maximum eigenvalue of C and see whether it is correlated to the maximum eigenvalue of C hat. So now I have to do a bit of calculations. So what are we going to do? Let's look, we want to study the eigenvalue, the maximum eigenvalue of C. So the eigenvalues of C are solutions of the determinant of Z times the identity minus C equal to 0. So when this is a function of Z, when this function is equal to 0, then Z is an eigenvalue of C. So lambda 1 is going to be the biggest solution of this equation. Now, what I can do, I can use I want to know how the maximum eigenvalue of C is related to the maximum eigenvalue of C hat, the true one. So what I do, I multiply this matrix. This is a L by L matrix. I multiply by T hat to the 1/2 on one side, and by T hat to the minus 1/2 on the other side. I can do that because the determinant of A, B, C is the product of the determinant of A times the determinant of B times the determinant of C. T hat is a positive matrix, so the determinant of T hat is positive. And so if I multiply this by a positive number, nothing happens. Actually, in this case, I put it to the 1/2 and minus 1/2, so they will cancel. But anyway, I could do it even with another power. OK. So now, when I do this product, what I get is the determinant of Z times the identity, because in the first term, I get T 1/2 times the identity times T minus 1/2, so I get 1, minus T to the 1/2 times C times T to the minus 1/2. Well, OK, I don't need. Let's erase this. I mean, we will remember that our estimator is the maximum eigenvalue of C. Okay. Now, what is this matrix here? I can write this matrix. Okay, let's write it more explicitly. So t to the 1/2 times c times t to the minus 1/2 is equal to t to the 1/2. Now c is the correlation matrix of the data. So it is 1/m times y transpose y. Remember, y is the matrix where I put all my data. So it's a matrix of L times M size. M times L. It's M times L. So y transpose is L times M, and y is M times L. So this is an L by L matrix. So this is L by L times L by L times this. Okay. And now I write t to the minus 1/2 as, so I get the 1/m here. Then I get t to the 1/2 times y transpose. This is a number, so I put it outside. Then I get y times t to the 1/2. And because I have t to the minus 1/2, I write it as t to the 1/2 times t to the minus 1. Okay? Now let me call x equal to y times t to the 1/2. So x is a matrix. What is the size of this matrix? It's again, this is m times L, this is L times L. So I get m times L again. So x is a matrix where each line y, here if I have a line, this is y1, y2, these are my data. What I'm doing is I am multiplying each data point by t, 1/2. So x1 is going to be equal to y1 times t to the 1/2, and so on and so forth. So I am applying a transformation to the data in such a way that, that I get x. Okay, then this thing is going to be 1/m. T is symmetric, so this is x transpose, because x transpose is t 1/2 transpose times y transpose, but t is symmetric. So this is x transpose times x. And now t hat to the minus 1 is c hat. Right? So what I get here is the determinant of z times the identity minus this thing that I call w times c hat. Okay? Now, what is w? Is it okay up to this point? So what I'm showing is that the eigenvalues of c are the same as the eigenvalues of c hat, which is the true matrix of the true, the one I would get for infinite number of data, times a correction. The correction is this w, and w is 1/m x hat x transpose x, where x is this matrix here. What are the lines of x? The lines of x are the data multiplied by t hat to the 1/2. So what is the probability of one of the x? Now the y are independently distributed with the Gaussian probability. So the x, which are linear transformations of the y, are also going to be independent variables. So each line is an independent vector. And the probability of x given t is what? It's going to be the probability of y where I apply the transformation. So this is going to be exponential of minus 1/2. So the probability of y was exponential of minus 1/2 y times t times y. And I have to put, apart from the proportionality constants, then I will normalize, I have to replace y with x. So x is y to the times t1/2, and so y is x times t to the minus 1/2. So I will write here exponential of minus 1/2 x times t to the minus 1/2, which is y, times t times y, which is again t to the minus 1/2 times x. So I get t to the minus 1/2 times t to the minus 1/2, which is the identity. So the probability of x does not depend on t. The normalization is a constant, so it's OK. And it's simply exponential of minus 1/2 x transpose x, which is sum over I of xi squared. So this means that x is a matrix of noise, of pure noise, that is, so x is a matrix of size m times L, where each element of the matrix is a normal, is a standard Gaussian variable with 0 mean and unit variance. Okay? So X is a pure noise matrix. Okay. So what we obtain is that the eigenvalues of the correlation matrix C are equal to the eigenvalues of W times C hat, where C hat is the true correlation and W is a noise matrix. Okay. So I can erase this line now. Okay, W is called the Wishart matrix, and is basically you can write it as 1 over m times sum over mu from 1 to m of x mu, let's say, x mu, whatever. I mean, let's put the indices. So Wij is 1 over m sum over mu of xi mu xj mu. Okay, so it's basically a sum of products of these Gaussian vectors. So this is called a Wishart matrix. It's a random matrix because the x are random Gaussian variables with 0 mean and unit variance. Okay. So our goal now was to study the biggest eigenvalue. And so we want to look to the biggest eigenvalue here. Now I want to obtain an equation for the biggest eigenvalue. Okay? How do I do that? I use the fact that I know C hat. I know that C hat is equal to 1 plus S hat E hat transpose. This was my original assumption, right? So I put it here, and I get here the determinant of Z times the identity minus W times the identity, which is W, minus S times S hat times W times E transpose. Okay? And once again, this must be 0, and I want to look to the biggest solution where this is 0. Okay? So I have to do some manipulation now. So now I'm going to make an assumption. I'm going to make the assumption that the biggest eigenvalue of C is not an eigenvalue of W. So if, okay, so I assume that that lambda 1, the biggest eigenvalue, that is the biggest solution of this, is not eigenvalue of W. If this is the case, then this thing, the determinant of this is non-zero, so this matrix is invertible. So I can invert it, so I can multiply this determinant by the inverse, and I write it as the determinant. So I basically factorize this term, and I get 1 minus S hat. So I multiply everything by the inverse of this. So I get z times the identity minus W inverse times W times E hat transpose. Okay? This is true if Z is not, so lambda 1, the thing I'm looking for, that is a solution of this, is not an eigenvalue of W. Okay, and so now I get the determinant of 1 minus something. This something is a matrix of rank 1, because there is this projector here. So if you apply this matrix to E hat, yes, but I'm assuming that it's non-zero, because I'm assuming that Z is not an eigenvalue of W. So I drop it. I mean, I'm sorry, yeah, there are constants at each step. So this is equal to 0, so I'm dropping all the constants on the way. So just this must be equal to 0. Thanks. So this matrix here is of rank 1, because if you apply this to E hat, you get something, but if you apply to any vector that is orthogonal to E hat, you get 0. So this matrix has all the eigenvalues equal to 1 except 1. So the determinant is going to be what? It's going to be 1, it's going to be 1, 1, 1, 1, 1, plus the only eigenvalue that is non-1 of this object. And so this is equal to 1 plus the trace of this. Sorry, minus the trace of this. Why? Because the trace of this is going to be the only non-zero element of this thing. Okay, so if you get a bit lost in the details, don't worry. The important thing is that you get the idea of the calculation. Okay. So you get 1 minus S hat times this trace, and now again, by the cyclic property of the trace, you can bring the E hat on the other side. So you get 1 minus S hat, and again, you have now E hat transpose times this, times W, times E hat. And this must be equal to 0. This was my condition. So in the end, I obtained an equation, let's write it here, for the biggest eigenvalue of C. So what I've shown is that in the end, 0 equal to determinant of this is equivalent, under the assumptions I made along the way, to the condition that this thing is 0, which means 1 over S hat should be equal to E hat transpose times 1 times this times E hat. Okay? So the biggest eigenvalue of C satisfies this equation. And in this equation, W is this matrix of noise. Okay? So now, to conclude the calculation, we can say that W will have eigenvalues and eigenvectors. So W is a matrix, L by L. It's a random matrix. I can diagonalize it, and I will get a sum over alpha of lambda alpha times U alpha transpose. So where lambda alpha are the eigenvalues of W, and U alpha are the eigenvectors of W. So if I plug this here, sorry, I should say one more thing. So now, okay, let's first plug this here. So if I plug this here, what do I get? So if W is diagonal in a basis, this is W times the inverse of this, which is also diagonal in the same basis. So what I'm going to get is sum over alpha. So W gives me a lambda alpha then I get Z minus W, which gives me Z minus lambda alpha. So what I'm saying is, if I work in the basis where W is diagonal, then all this matrix is diagonal, and the eigenvalues of this matrix are the eigenvalues of W divided by Z minus the eigenvalue of W. And then I have the projector U transpose with the E transpose. So I get E scalar product with U alpha square. Because here I get E U E. So this is the scalar product of E with U, and this is the scalar product with E, of E and U. Okay? Okay. Now I use an important property, which is that because X is pure noise, the X are rotational invariant. If I make a rotation of the space, because the probability of X is the exponential of minus 1/2 x squared, where x is a vector, it only depends on the norm of X. So I can rotate X as I want, and statistically nothing will change. So the probability of having a matrix W and of having a matrix W that is obtained by rotating the X is the same. This means, because W is rotational invariant, I mean, not W, but I mean, because X is rotational invariant, the probability that the eigenvalues of W, I mean, W is symmetric, right? So you can diagonalize it, and the eigenvalues, the eigenvectors are an orthonormal basis. So you have an orthonormal basis. Every time you draw a W, you get an orthonormal basis. But the probability of any rotation of the basis is the same because of the rotational invariance. So these eigenvectors have the same probability of being pointing in any direction. What does this mean? That if I take the component of these eigenvectors along a given direction, so let's fix this direction E hat, for example, like this, and I want to project U on E hat, but U has the same probability of being pointing everywhere, so the probability that this is positive or negative is the same. So the expectation over W, over the X of this thing has to be 0. Right? Okay. Also, the expectation of the square of this must be the same for all the alpha, because I can rotate the basis as I want, so the eigenvectors are all the same, statistically are all the same. So this is a constant, C, that does not depend on the specific eigenvector I choose, right? And so, but what is this constant? I know that the sum over alpha of E times U squared is also equal to the sum over alpha of E transpose U transpose E. And the sum over alpha of this is the sum of the projectors. It's an orthonormal basis, so this is the identity. The sum of U alpha transpose is the identity. So this is equal to 1 because E is a unit vector. So the average of this, which is the average of this, blah, 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 must also be 1. So if these are all equal and the average of the sum must be 1, they must be all equal to 1 over L, where L is the number of vectors that you have, right? So this is an important property, because then this thing is a random number, but it's a random number with 0 mean, and, sorry, without the square, but when you put the square, this is a positive number whose average is 1 over L. And so again, you can say that this thing, when L is large, now I'm taking L to be large, for each eigenvalue of the matrix W, there will be, I mean, in a range, there will be many eigenvalues that are very close, and they have different eigenvectors. So this will make an average. And OK, you can discuss the details, but let's skip the details. So you can replace this by the average. And you get 1 over L sum over alpha of lambda alpha times divided by Z over lambda alpha. OK? So you can forget, if you want to know the top eigenvalue of C, you can forget about the eigenvectors, and you just need to know the eigenvalues of W. OK? So now what we need to do is to compute the eigenvalues of W. And just to write this in a better way, so the condition for to find the top eigenvalue of C becomes that 1 over S should be equal to this thing. So 1 over L times the sum over alpha of lambda alpha divided by Z minus lambda alpha. And this sum is from 1 over L. And now the idea is that you can make a histogram of the eigenvalues. So when you are at finite L, you will have eigenvalues. But then you can make a density. So if you call rho of lambda the density, so the number of eigenvalues that are close to a certain lambda, this sum, as usual, this is like a density of states. This sum will become an integral when L is large. So you will get the integral over lambda of the density of eigenvalues divided by this. OK? So what you need to know is the density of eigenvalues of this matrix W. Here you can add and remove a Z. And so this thing can also be written as -1, because here you have Z minus lambda divided by Z minus lambda with a -1, and the integral of this is normalized to 1 by construction, plus the integral over lambda of rho of lambda, so plus Z, this one. OK. And so this quantity is usually called G of Z, and it's the resolvent in random matrix theory. So what we need to finish the calculation is to know this quantity for this W matrix. And then we are done. OK? Now, the calculation of this quantity takes a bit of time, so I will not do it today. We can discuss if you want to see it or not. So let's finish the discussion for today, and then we decide what to do next. So you need to compute this thing, where rho of lambda is the density, if you want, is the probability that one eigenvalue of the matrix W is equal to lambda. And you have to compute this. So you can do it, and what you get is that G of Z is a simple thing, is Z plus R minus 1 minus square root of Z square minus 2Z R plus 1 plus 1 minus R square divided by 2 R Z. So where R is always number of parameters, number of size of the problem divided by number of data you have. So you can compute this thing. This will give you, from this you can get the spectrum, rho of lambda, which has this shape. So it's centered in around 1, and then it has this shape. Yes?
I missed your explanation. How did you write this?
No, I didn't do it. So you have to do it. I cannot do it today.
Yeah, I mean just have rho of lambda.
I don't have rho of lambda. So I need to compute. So I need to compute this object, integral of rho of lambda divided by z minus lambda. So where rho of lambda is the probability that the matrix W has one of the eigenvalue equal to lambda. I don't have it, so now I'm just telling you this is known. And if you want, tomorrow I can show you how to do this. So we can discuss what to do tomorrow. But for the moment, let's take it as a result. So in the end, what we have to solve is this equation. In order to get, again, I want to get the maximum eigenvalue of C. So I have to solve that 1 minus S is equal to minus 1 plus Z G of Z. Okay? So if you plot this function, so G of Z is this function. You plot minus 1 plus Z G of Z, and what you get, so let's call this function f of Z. So if I plot f of Z, what I get is that it has, this is Z, this is f of Z, and this function is something like this. Up to a point. Here, this is lambda plus, which is also this lambda plus here. It's the edge of the spectrum. Lambda plus is equal to 1 plus square root of r square. So, I mean, below lambda plus, when z is smaller than lambda plus, the argument of the square root becomes negative. So G is not defined. I mean, it's defined, but it becomes imaginary. But we don't care about z smaller than lambda plus, because all this calculation was done under the assumption that z is not an eigenvalue of W. So if z is smaller than lambda plus, then z is an eigenvalue of W, and my calculation is wrong. Okay? So let's restrict to z bigger than lambda plus. The function is something like this. And I want to find the value at which this function is equal to 1 over s hat. So this will correspond to a certain z. And this will be my eigenvalue, my estimator, so 1 plus s star. The value of the top eigenvalue of C is my estimator for the true one. Okay? So you can solve, and sorry, I forgot to say, when z goes to lambda plus, the function here, the function f is equal to 1 over square root of r. So what you see is that you can solve for s star, provided s hat is bigger than r square. Otherwise, you don't have a solution. So what's the behavior of your estimator? So you have a phase transition as a function of, for example, as a function of s hat. So s hat is the signal, right? Is the difference between the true top eigenvalue and 1. The true top eigenvalue is 1 plus s hat. So s hat is the signal you want to learn. And r is a measure of the noise, is the amount of data that you have, how much noise. The more you have data, the less is the noise, and the smaller is r. So when s hat is bigger than r square, so here there is r square. Square root of r. Messing up there. So when s hat is bigger than square root of r, 1 over s hat is smaller than 1 over square root of r, and you have a solution that is bigger than lambda plus. Okay? So if this is lambda plus, so this is S star, okay? Here you get lambda plus, which is 1 plus square root of r square. So if S hat is bigger than square root of r, you get S star, you get that 1 plus S star is bigger than lambda plus. And so you get something like this. And when, I mean, asymptotically, when S hat becomes very large, S star goes to S hat. So this becomes, so you get the correct result. But when S hat goes to square root of r, below that point, you don't have a solution anymore for S star, in the sense that the assumption we made that the top eigenvalue of C is not an eigenvalue of W is wrong. And so basically the top eigenvalue of C is going to be the top eigenvalue of W, which is lambda plus. So you get this. So this means this is what is called a retarded learning phase transition, because the learning is delayed by the noise. So when the signal is smaller than the noise, here the measure of noise is square root of r, or r. When the signal is smaller than the noise, you cannot learn. So the top eigenvalue of your matrix, C, the data matrix, is given by lambda plus, which is the top eigenvalue of the noise matrix. So the top eigenvalue is dominated by the noise. When the signal is large enough, you start to learn. And when the signal is very big, you have that S star is exactly equal to S hat. Actually, you can explicitly write S star is going to be S hat plus R over S hat square. So if you, yes, so if you solve the equation 1 over S hat equal to f of z and you use the shape of, so you see when S hat goes to infinity, these terms become subdominant and you have S star equal to S hat. The other thing you can compute is the scalar product between the maximum eigenvector associated to C and the true maximum eigenvector, which is E hat. And you can show that this is 1 minus R over S hat square divided by 1 plus R square, I think. No, without the square. So this quantity is 0. This is for, all this is for S hat bigger than square root of R. So in the regime where you can learn. So you see that if you plot the scalar product as a function of the signal, if you plot the scalar product of the of your top eigenvector with the true top eigenvector, you get 0 up to this point, because basically I mean, this vanishes in this point and then it's 0. And then you get something like this that goes to 1 when the signal goes to infinity. Okay? So the message of this long calculation is that when you are in a regime where L, the size of your data, and the number of data you have goes to infinity, keeping fixed the ratio of the two, you can have a phase transition as a function of the parameters, in this case the signal to noise ratio, between a phase where you cannot learn anything and a phase where you can learn something. And of course, the more the signal is big and the more you can learn. So we have seen this in this specific example where you have Gaussian variables with a correlation, with the true correlation that has all the eigenvalues equal to 1 except 1 that is bigger than 1, and you want to learn that one. But this is more general. I mean, this happens in many, many problems in inference where you have a transition between a phase where you can learn and a phase where you cannot learn, and you can have more complicated situations. So now, tomorrow I wanted to show you an application to some biological data of this. I mean, this is basically principal component analysis. So I can do that. And if you want, I don't know, I know that the PCS students already know this, how to get this through the cavity method from the course of Jean Barbier, I think. If you want, I can try to show you how you can get this with another technique that is called the Dyson-Brownian motion. So I can do this tomorrow, or I can skip it and I can give you the notes if you want. And I can discuss more like the biological part, and I can show you also how to do PCA when you, instead of having all the data at once, you get one data after the other, and you have to use the data online as you get them. How can you do PCA in that case? So maybe if you have a preference, let me know. I mean, not now, but even in the break or by email or whatever. Let me know what you would prefer, and we can adjust for tomorrow. Sure. Let me switch this off.